All right, I want to go over the calendar, but again, if you haven't put your phones up on the wall, you got to do that for me. And I hope to have your quizzes graded and return to you hopefully Wednesday-ish. So we'll get that back to you Wednesday, Thursday. We're going to do the second half of Unit 1, overall limits. Let me talk about kind of briefly what we're going to do. Continuity and discontinuity. We're going to talk about functions that are continuous and what are the conditions that's going to allow us to confirm that a graph is going to be continuous through a point. We have something called squeeze theorem, which is, I think, pretty straightforward. Intermediate value theorem, I think it's going to be, I think it's just going to naturally make sense. We just have to kind of know how to justify these types of situations. And then we're going to talk about, we talked about limits as we approach a real number. We're going to talk about limits as we approach infinity. Basically, how do we confirm that there's a horizontal asymptote? We kind of know how to do this already, but just have to get used to that limit notation. And then we can finish that off on Friday, and then we can begin our test review. So I'll give you guys a test review packet on Monday. We'll work through 2 days and then test next Wednesday. Okay. There's homework each day this week, and they're all in your packets. And now we'll make sure to just kind of go over, make sure that we know where to find these homework problems and and also on the website for checking our answers. Okay, so notes. All right, page 11. So a one-sided limit describes the function's behavior from the left or the right side of an x value. So let's say we had a function here, a piecewise function. You got x squared that is to the right of 1. So that's the kind of a parabola here, but it's not showing the full parabola. It's only showing that parabola to the right of 1. And then you got x plus 3. That's a linear graph. And that linear graph is only showing itself to the left of 1. So we still have a function, but we can tell that the graph is disconnected. And if I ask you, what is the limit as x approaches 1? What would you say? The limits in terms of, if we, okay, let's say you didn't have the function in front of you. You're looking at the graph here. What would you say the limit is as we approach 1? Okay, why is that? Of discontinuity, right? We talked about how visually we used arrows, right? And the arrows indicated that if they're not headed to the same y value, then we have an issue, right? Even though the point exists, the arrows are obviously not headed towards the same y value. They're not approaching the same y value. Therefore, the limit does not exist. Okay, so we know that to be true. We learned that on your quiz. You guys demonstrated that in your when I gave you the graph and you were asked to find whether the limit exists. But we used arrows here as a way of indicating whether we want to look for an agreement between the two arrows. Now, this is a kind of an informal way of demonstrating basically a one-sided limit. So one-sided limit is just asking, what is the arrow from approaching from the left, or what is the arrow approaching from the right? And also, we now have a more formal way of representing those arrows that we were initially doing just, visually. And the left arrow, or the arrow that's headed on the left side headed towards the right, this we call a one-sided, this we call a left-handed limit. So this is where if we're having approaching 1 from the left side of 1, you see that negative sign that is up in the exponent, that is indicating what this arrow is doing. Right? So where is this arrow headed? What y value is that arrow headed? Getting closer towards what? 4, yeah. So we can say that the one-sided limit as we approach 1 from the left side is equal to 4. What about the right-handed limit? What about the one that we start on the right side of 1 and then we head left towards 1? Where is that arrow headed? Towards y value of 1. Okay. So we know how to do this because we were talking about this last week, but now we should have to know, okay, this is the notation that is representing what we were doing with the arrows. So we know that in order for our full limit to exist, these arrows have to move towards the same y value. So therefore, if the limit is going to exist, the limit as x approaches c from the left side of c of f of x has to equal to the limit as x approaches c from the right side of c. What that indicates is we plot points on either side of our target. Are the arrows headed towards the same y value? If they are, we can conclude that the full limit exists if the arrows or if the one-sided limits are in agreement. Okay, so we're going to talk about this idea of continuity. So continuity means, can I walk along the graph without any interruptions? Can I draw the graph without ever lifting my pen or pencil? If so, the path of the graph is continuous at that point. So if I can sketch a graph without lifting my pen or pencil, then my graph is continuous. Right? So it's easy to recognize it on the graph, but we're going to be using limits to prove whether a graph is continuous at a point. So here are the 3 conditions, and then we can talk through them. The first is, if the graph is going to be continuous at a point, it's got to meet these 3 conditions. First, the point has to exist. F of c is defined. So we're going to find that point, and the side of it exists. Second, the limit has to exist. And sometimes we have to look at the one-sided limit. We have to look at the arrows and see if they are in agreement. There are times where we have to rely on the one-sided limits. There are other times where we can just write the limit once. And I'll talk about situations where we can use one limit statement or where we have to rely on two limit statements. But either way, the limit has to exist. And third is, does the limit live where the point lives? If they do, then the graph is going to be nicely connected through that point, and our graph is going to be continuous. So let me just draw a example or graph kind of demonstrating these three conditions. Let's say we had a C value, just some arbitrary X value on the graph. F of C is defined, so if there was a point here, then it would pass the first condition because the point is defined. Second condition, let's say the graph looks like this. Right? Would the limit exist as we approach C? With this graph, if I were to look at this graph. Would the limit exist? Yes, right. If I pick points on either side of my graph, they're obviously pointing towards the same y value. They're both pointing towards the whole. So then the first condition passes, second condition passes, but does the third condition pass? Does the limit live where the where the point lives? No. So this one, it would fail, right? The third condition would fail because that point is not filling in where that hole is. Now, when you get to the third condition, you're not creating any new data. You're just looking back at what you've gathered from 1 and 2 and see if they're in agreement. So really, it's just 1 and 2 that the first and second condition are the only ones where you're actually gathering data. And third condition, you're just looking back at what you've gathered and just seeing if they're in agreement. Okay, we're going to talk about what type of discontinuity this is. And the first is we have a type of discontinuity called hold continuity or a removable discontinuity. This is a graph with removable discontinuity is one that can be made continuous by filling in a single point. So this one will be removable discontinuity, and so would this also be a removable discontinuity. Okay. So we can tell that if we're going to get to a situation where there's going to be a hole in the graph, it's got to pass the second condition, and it's got to fail the third one. Okay, so a removable discontinuity passes the second condition, but fails the third condition. Now, some of you may be thinking, wait, what about the first condition? The first condition, whether the point exists or not, it's not going to determine whether we have a removable discontinuity. Because if you look at this graph has no point defined. This graph has a point defined, and both of these have a whole discontinuity. So the first condition doesn't really distinguish between doesn't distinguish us being able to identify whether our graph has removable discontinuity. It's got to basically pass the second one, but fail the third one. The limit exists, but the point is not defined where the limit is. Okay, next page. We also have something called a non-removable discontinuity. And this is a step or a jump discontinuity. This is a discontinuity where the graph jumps from one connected piece of graph to another. So a non-removable discontinuity is going to fail the second condition. It's basically where the limit doesn't exist. So we can see that is the case here, right? Let's look at the one-sided limit, where we can draw arrows. As we approach -1 from the left side of -1, we can see that the y value is headed towards 3. As we follow the arrow on the right, headed towards -1 from the right side of 1, we see that this arrow is headed towards a different y value, and therefore the limit does not exist. Anytime the limit doesn't exist, we categorize that as a non-removable discontinuity. Right. Well, let me highlight, let me revisit the continuity conditions, and then we can look at 3 examples and practice writing out those conditions. So if the first condition fails, obviously the function is not continuous because the graph is not defined at that point. But we continue to test the next conditions because we want to categorize between, is it a discontinuity because it's removable, or is it a discontinuity because it's non-removable? We still don't know which category we're dealing with, even though the function is already going to not be continuous, because if the first condition is going to fail. But so basically, if the first condition fails, we keep going. Okay? We haven't had enough information to categorize yet. If the second condition fails, then we know the limit doesn't exist, and therefore it must be a non-removable discontinuity, regardless of what happens with the first one. Okay. Now, we only want to test the third condition if the second condition passes. If the second condition fails, we stop because we already know what type of discontinuity. We only go to the third condition if the second passes. So if the limit does exist, we go to the third condition. So if the second condition passes, but third condition fails, then we must have a removable discontinuity. And obviously, if all 3 conditions pass, then the point exists, the limit exists, the point is filling in where that hole is, and the graph is continuous. All right, so let's look at some class examples here. Using continuity conditions, determine the reason why the following graphs are discontinuous, then categorize as removable or non-removable discontinuity. Now, the C value is always going to be easy to identify. You're never going to have to guess what the C value is. It's always the point that is in question. If it's a piecewise function, like the first example, you basically look at the X value that they're identifying, and that's going to be your C value. And if you look at the graph, you can just find where the point is obviously having issues. So here, our C value is at 5. We highlight that point. We're going to go through these conditions and then practice writing them out. So first condition, does the point exist? What would you say? F5. So can we say f of 5 is defined or undefined? Defined. Okay. Where's f of 5? Where's the order pair? At 1. So it'll pass the first condition, so we keep going. Okay. Second condition, does the limit exist? No. Right. And we know that because if I pick points on either side, and if I draw an arrow towards my destination, the arrows are not pointing to the same y value. The limit doesn't exist. But we want to translate those arrows into a formal way of writing it out. So we're going to use one-sided limit. So we're going to say this: limit as x approaches 5 from the left side of 5 of f of x. Make sure we are writing out that f of x. So this notation is indicating what we're doing with those arrows. Does not equal 2, because this one's approaching 2, the other's approaching 1. Does not equal to limit as x approaches 5 from the right side of 5 of f of x. This notation is basically what this arrow is doing. And therefore, we can conclude that because the one-sided limits are not in agreement, the full limit also doesn't, we can say doesn't exist. So if the second condition fails, do we go to the third condition? We stop, right? And we say, we can conclude what type of discontinuity? Yeah, non-removable. Now, we only are testing discontinuity at a point, so make sure that we don't just say non-removable discontinuity, that we indicate the point that we're talking about. So non-removable discontinuity at x equals 5. Okay, second condition. Sorry, part B. Again, the point that is in question is again at 5. We can tell there's a hole, but we're going to go through our conditions. First thing, what can we say about f of 5? Defined or undefined? Undefined. Okay. Now, we already know the graph is not continuous, but we haven't proved what type of discontinuity yet, so we're going to keep going. Does the limit exist? Yes, right. We can tell that the arrows from both sides are going to head towards the same y value. And if the limit exists, let's just go ahead and write that limit statement. Limit as x approaches 5 of f of x is equal to what? Maybe it's hard to tell. They're both headed towards, let's say, 1, right? They're both headed towards a y value of 1. So it passes the second condition. Do we keep going? Yes, right. So keep going until we reach something that fails, then we can stop. Now, the third condition is asking, does the point live where the limit lives? So when we get to the third condition, we're not going to create any new data. We're just looking at what we've gathered and seeing if they're in agreement. Are these in agreement? Is undefined the same thing as 1? No, they're not. So we know it's going to fail the third condition. Now, the way I want you to write it is I don't want you to say undefined doesn't equal to 1. That is not as clear as we can be. So I want you to write out the third condition exactly as you see it. The only thing you're going to replace is the C value. So if you replace C value, in this case, what's our C value? 5. So you're going to write out the exact same statement, just replace the C value with 5, and that will indicate that we are justifying that third condition. Now we're going to say doesn't equal to, right? Not equal to, but so we're going to say limit as x approaches 5 of f of x does not equal to f of 5. Therefore, we know the third condition fails. And what type of discontinuity can we categorize this as? Removable. And always, we want to make sure we specify the x value. Okay. Make sure we specify the x value when we identify the discontinuity. All right, third scenario. The point in question is at 3. We can tell that there's a vertical asymptote there. So let's go through our conditions. F of 3. What can we say about f of 3? Defined or undefined? Undefined. There's a vertical asymptote there. There's no point. So we already know the function is not continuous, but we want the category. So we're going to keep going. Does the limit exist? No, it doesn't exist, right? We know that from the left and from the right, they're both approaching positive infinity, but we know that positive infinity is not a real number. So we can say the limit as x approaches 3 of f of x is equal to infinity, and therefore the limit does not exist. Right, so even though we say equals infinity, we know infinity is a subcategory of does not exist. So can we stop or do we keep going? We stop, right? We know what subcategory. We know we're dealing with a non-removable. So a jump discontinuity and a where there's a vertical asymptote, these are both same subcategory. These are both non-removable discontinuity. These are both situations where the limit doesn't exist. Okay, part D. It says find the point of discontinuity for the function f of x equals x squared minus 9 over x minus 3. Is it removable? If so, what will we need to do to allow this function to be continuous? Where do we find discontinuity if we are looking at a rational function? Where do we look if we're looking to see where a graph is maybe as a whole or an asymptote? Numerator or denominator? Denominator, right? So this x minus 3 can be either a whole or an asymptote depending on whether it stays or it gets canceled out. But we know that there must be a discontinuity at 3 because it's in the denominator, right? Anything in the denominator is going to cause issues. So we know that that's our C value. Our C value is at C equals 3. Okay, so we're going to go through our conditions and see if we can prove what type of discontinuity just by going through each of our conditions. All right, first condition, does the point exist? F of 3, does f of 3 exist? So if I plug 3 into the function, what am I going to get? Defined or undefined? What happens when we plug 3 in for x? 0 over 0. Is that defined or undefined? Undefined, right? So the point doesn't exist, so undefined. All right, second condition, does the limit exist? Well, let's just apply the limit for our function, right? So treat this like a quiz problem that you guys saw last week. What's our first step? Direct substitution, right? What does direct substitution tell us? There's a hole, which means we got to keep going, right? That means the limit does exist. And what would you do next? Factor, difference of squares. Okay, what do you see? Cancels out. Reevaluates. What do we get? 6. So the limit does exist, right? The limit does exist. Do we keep going or do we stop? Keep going, right? So now the third condition, does the limit live where the point lives? Are these in agreement? No. So we're going to write out our statement like how we did, where we write out the third condition the exact same way as we see in the definition. We just replace the C with the C value that we're dealing with. So we're going to say limit as x approaches 3 of f of x does not equal to f of 3. Therefore, what type of discontinuity are we staring at? Removable. One more thing here is if it is, we did confirm, is it removable? We know it is removable. If so, what would we want to set f of x equal to so that the function is continuous? So what would f of 3 must be equal to if we want this graph to be continuous? Yeah, f of 3 has to be equal to 6 in order for these to agree, in order for this to pass. Yeah, so it says, how would you redefine? So we would redefine f of 3 to be equal to 6 in order for continuity at x equals 3. Let me do a few of the homework problems with you. So this is coming from the exercise pages. So I want you guys to do it on a separate sheet. If you need spreadsheet sheet, you can grab one from either of my shelves, or you can grab your own notebook paper. So this is that 1.3 exercise problems. That's a few pages down. Actually, I'm going to do problems that are not your homework, so that you can use this as a model as you try them. Let's try 23 here. Okay, the directions, it says determine whether the function is continuous and at C, and we want to prove using continuity conditions. So let me write 23 out here. Now, it specifies that C is equal to 2, but they don't have to say this. If it's a piecewise function like this, you know that whatever x value they're referring to is going to be your C value. Okay, we're going to prove whether the function is continuous at x equals 2, but we're going to have to justify it through the work of our conditions. So let's go through our conditions here. First condition, does the point exist f of 2? And if I want to find f of 2, which piecewise am I going to plug in? Yeah, the first one, because I see that equal sign that is defined for the first piecewise. So 2 in for x, what do we get? 9. 4 plus 5 is 9. So it passes the first condition and we keep going. Even if it fails the first condition, we still keep going, right? It says determine continuity, but I want us to also determine discontinuity, or the type of discontinuity, if we run into that issue. So second condition, does the limit exist? We have two different graphs here. So we basically have to look at the arrows and see if the arrows are in agreement. And because you see different functions or different graphs on either side of my C value, I got to rely on one side of limits. So I'm going to have to do the approach from the left and the approach from the right. We're basically, if the graph was in front of us, we're going to have to plot the 2 points on either side and draw the arrows. And the way we draw arrows without the graph is we use the limit, one-sided limit notation. So we're going to look at the approach from the left side of 2. So we're going to start at a point on the left side of 2, and we're headed towards 2. Which piecewise is this referring to? What's to the left of 2? The 2x plus 5 or the 4x plus 1? Yeah, so go ahead and write out that expression, 2x plus 5. Okay, direct substitution. Don't worry, that negative just indicates where we're coming from, but we're always going to do direct substitution first. Well, I mean, we're just going to always plug in that integer value. So where's the graph headed towards from the left side? I plug 2 in. Still what? Still 9. Okay, let's look at it from the other side. The approach from the right side of 2, so 2 with a plus. Which one is this referring to? 4 plus 1. What does this give us? 9. Are the arrows in agreement? Yes. So we're going to make a conclusion. We're going to say the full limit exists. So we'll say limit as x approaches 2. You don't have to write out the entire piecewise. Just reference this whole thing as f of x. We conclude that these are in agreement. Therefore, my full limit is 9. Do I keep going? Yes. Second condition passes. It can't be a non-removable discontinuity. I'm just looking at the third condition. So third condition, how do we decide what to do with the third condition or whether the third condition passes? We compare the what? First two, are they in agreement? Yes. So we're going to say, we're going to write out the third condition. We're going to say they're equal to each other, and we're just going to write out that third condition with a c replaced. So we're going to say the limit as x approaches, instead of c, we'll say 2 of f of x is equal to f of 2. You don't have to say that this is equal to 9, that's equal to 9. We've already established that they're both equal to 9. So this is enough. If this was an AP exam problem, this would be sufficient for us to confirm that, therefore, the function is continuous at x equals 2. And so this is how we use continuity condition to prove or to justify whether a graph is showing connectedness or they're disconnected, and if they're not connected, what type of discontinuity can we categorize? Okay, let's do 24 here. I'm sorry, 26. I want to do a problem that has a setup that is similar to your homework. Okay, I do want to talk about what these restrictions tell us about the graph. If you see x is less than 1, obviously it's to the left of 1, but it's also, this is a connected piece of graph. That means everything that is less than 1 is all contained within this 3x minus 1. So we know that this is going to be a connected piece of graph. Okay, so I want to just kind of make sure that we understand what they mean here. Now, this one is only defined at x equals 1, so this is indicating just a what? It's just a point, okay? And then 2x if x is greater than 1, so anything greater than 1 is going to be contained within this 2x. This is going to be a graph. So you got a graph, a point, and a graph, and we're just wanting to know, are they all connected in a way that we can confirm continuity, and if not, what type of discontinuity? So first condition. And the c value is always the point in question, so our c value is at 1. So we first have to find f of 1. What's f of 1? 2, right? That's just the point defined there. Second condition. Does a limit exist? We have two different graphs on both sides of 1. So we got to do one-sided limit and go through those notations. So let's start with the left side of 1. Approaching from the left side of 1, which function is this referring to? 3x minus 1. Okay, plug 1 in. What do we get? Okay. 2, right? 3 times 1 is 3. 3 minus 1 is 2. Okay, keep going. We look at the limit from the other side of 1. We also get 2. Limit exists, right? They're in agreement. So we'll write out that full limit statement. X approaches 1 of f of x. There's no need to write out your full piecewise. You can just call it f of x is equal to 2. Condition passes. Is the third condition going to have any issues? Are we going to be, is it going to pass the third condition? Yes. So we're going to write out, don't say 2 equals 2. We're going to write out f of 1, or doesn't matter which one you say first, but we're going to basically write these two statements out and set them and say they're equal. And then let me do 36 with you, 36. Okay. We're just stepping through a continuity condition again. And so the direction here says, determine if there's a removable discontinuity. We're going to go through our continuity conditions. And if the function is not continuous, can we redefine f of c so that the graph is continuous? Again, the equal sign indicates that's just a point. And you have connected parts of graph on either side of -1 that's defined using different functions. All right, we know the point in question is at -1. So f of -1 is equal to 0. Second condition, we have less than, greater than. On either side of -1, they're different functions. We got to rely on one side of limit. We got to basically plot the points on both sides and see if the arrows are headed towards the same y value. From the left side of 1, we're using the first piecewise. Oh, sorry, approaching -1. -1 from the left side. Right? What happens if I do direct substitution? Yeah, -1 in for x. What do we get as a result? What's the result of our direct substitution? -4, yeah, 1. -1 squared is still 1. And then 5 times -1 is -5. 1 minus 5 is -4. From the right side of -1, we know that's talking about the x minus 3. What do we get here? also -4. What can we conclude? That the what? The one-side limits, are they in agreement? Yes, therefore, the full limit is also exists, right? So now we can drop the plus or minus. We can just say f of x is equal to limit is equal to -4. Make sure that we're always, that we don't just say the limit as x approaches -1 equals -4. We need to have something in place. We got to refer to what we're talking about. So first condition is good. Second condition is good. Third condition, is it going to pass or fail? Fails, right? So even though, so as justification, we're not going to say 0 doesn't equal to -4. We're going to say that these are not in agreement. We're going to just talk about where they're coming from and say they're not in agreement. So we'll say the limit as x approaches -1 of f of x does not equal to f of -1. That's how I want you to write it. All right, therefore, what type of category can we give this? Removable at x equals negative. And the final direction that it asks is define f of c so that the function is continuous at x equals c. How can I redefine f of -1 so that the hole is filled in? Make f of -1 equal to what? -4, yeah. So redefine f of -1 to equal to -4 to make f of x continuous at x equals Okay, 35 is your homework. Let's end with that. So I know this is going to make your homework be out of order, but it's fine. So let's do 35. Let me just walk around and see if you can justify each of the statements like how we did 36. Even if you're able to categorize it correctly, I'm looking for your notations. So I want you to practice writing out all these notations on the test. I'm looking for notations as much as I'm looking for the conclusion that you're reaching. This like full variable expression. Do 1 plus x. Okay, plus 2. Sorry. That's correct.
Oh.
So they've already agreed, but go ahead and find out what they actually bought. So write it out like this, where we're actually finding those values before we make that conclusion.
So the order pair is that order pair 1, 4. The one side limits do show agreement. We know the full limit does exist. In the third condition, we can obviously tell the point is not living where the limit lives. Removable discontinuity, and if we want to redefine, in order to prove, in order to allow continuity, redefine f of 1 to be equal to 2. Okay, so check your calendar for the rest of your homework problems. Come up and get your phones. Cool. Okay, appreciate it. I'll mark it down. Thanks.
I like there for one.
That is fine. Yep, implementation looks good. Thank you. Thank you.